Welcome to The Explainer. Today, we're doing a full chapter explanation unpacking the seriously cool foundational concepts of electric charges. We're going to take a journey together from those everyday static shocks you've definitely felt, all the way down to the invisible fields that literally govern our universe. It's a fantastic topic, so let's get right to it.
Here's our roadmap for today. We'll start with the spark of static electricity, look at properties of charge and Coulomb's law, map out electric fields and dipoles, and wrap up with a really cool AI tool to help you master this material.
All right, Section 1, the spark of static electricity.
Let's kick things off with something I know you've experienced. You're sliding out of your car seat, you reach for the metal door, and zap, right? It's totally startling. But that little jolt perfectly illustrates what happens when built-up electric charges suddenly discharge right through your body.
And it's wild how these everyday things connect the tiny to the massive. Think about it, the crackle when you pull off a synthetic sweater, or the literal earth-shaking power of a lightning strike. They are all driven by the exact same thing, static electricity. Now, static just means these charges are hanging out on an insulating surface. They aren't moving. Well, not until they find a path to discharge anyway.
Since we can't actually see these charges with our own eyes, scientists had to get creative. Historically, they used this brilliant little device called a gold leaf electroscope. Basically, when a charged object touches that metal knob on top, the charge travels down into the box and hits two incredibly thin gold leaves. Since like charges repel each other, the leaves push apart. They literally diverge. The wider they spread, the more charge there is. It's such a simple, perfect visual for something completely invisible.
Moving right along to Section 2, properties of electric charge.
Okay, let's zoom way into the subatomic level. Whether a charge is positive or negative, it plays by three main rules. First up, additivity. This just means the total charge of a system is the simple algebraic sum of its individual charges. You just add the positives and negatives together. Easy enough, right? Second is conservation. If you have an isolated system, the total net charge is locked in. It remains perfectly unchanged no matter how things rub or interact inside. You literally cannot create or destroy net charge. And third, quantization. This is the idea that charge isn't some smooth, continuous fluid. It's grainy. It always comes in distinct steps, exact multiples of a basic unit we call E, which is the charge of a single electron or proton.
And that brings us to a quote from our source chapter that just kind of blows my mind. It says, "Quantization of electric charge is a basic, unexplained law of nature. Interestingly, there's no analogous law on quantization of mass." Think about that for a second. We think of mass as continuous, right? You can always slice off a tiny fraction of a gram. But electric charge? Nope. It strictly exists in discrete steps. As for why? Physics actually doesn't have the answer yet. It's just a fundamental, unexplained law of the universe. How cool is that?
All right, Section 3, Coulomb's law and force.
Now that we know what charges are, how do they actually interact out there in space? Enter Coulomb's law. This defines the mutual electrostatic force between two-point charges. We all know the old saying, like charges repel, unlike charges attract. But the math here tells us that this force is directly proportional to the product of the charges. And, here is the kicker, it is inversely proportional to the square of the distance separating them. So if you move two charges twice as far apart, the force doesn't just cut in half. It drops to a quarter of its original strength. It fades out really fast over distance.
To really wrap our heads around the sheer scale of the electrostatic force we're calculating here, we need to compare it to something familiar. Let's stack it up against gravity, Newton's law. Both forces operate over a distance. Both follow inverse square laws. But who wins in a head-to-head matchup?
Take a look at this number, 10 to the 39th power. That is a 1 with 39 zeros behind it. That's the ratio of the electric force to the gravitational force between a single proton and an electron. It is absolutely staggering. It shows just how overwhelmingly dominant electrostatic forces are at the atomic scale. Honestly, it's the electric force, not gravity, that's holding the atoms in your body together right this very second. But you know, the real world is rarely just two neat little point charges sitting in a vacuum. When we have a bunch of charges, we use something called the superposition principle. Basically, don't panic when you see complex systems. The total force on any one target charge is just the vector sum of all the individual forces acting on it. You just calculate them one by one using Coulomb's law, add the directional arrows up, and you've got your answer.
Section 4, mapping the electric field.
So try this thought experiment.
If we suddenly snatch away a test charge, what's actually left in the empty space around it? The answer is the electric field. It's an elegant way of characterizing the electrical environment of a system completely independent of any test charge you might drop in later. Imagine an invisible, charged atmosphere extending everywhere in space around a source. If a new charge wanders into this environment, it's the field itself that pushes or pulls on it.
And here is where it gets really fascinating, because this concept bridges electrostatics with the gritty reality of relativity. Electric fields aren't just a math trick. They solve a massive physical problem: time delay. If I wiggle a charge right here, a second charge a mile away doesn't instantly feel the change. Why? Because absolutely nothing travels faster than the speed of light. The field perfectly accounts for this. The first charge moves, creates a ripple in the electromagnetic field, and that ripple travels out at the speed of light until it eventually hits the second charge. It's like throwing a rock in a pond.
Which brings us to Section 5, dipoles and field lines.
Okay, so how do we visualize these invisible environments? We look at specific setups, like the electric dipole. A dipole is exactly what it sounds like: a pair of equal and opposite charges. You've got one positive Q and one negative Q, separated by a specific, small distance we usually call 2a. Finding the field for a dipole is a classic textbook staple for a full chapter explanation like this. You usually end up calculating the forces along its central axis and then perpendicularly through its middle, known as the equatorial plane. And looking at this gives us a beautiful roadmap of what that field actually looks like. These are electric field lines. By convention, these continuous curves always start out at positive charges and dive into negative charges. But the real secret is in the spacing. The density of those lines tells you the field's strength. Where the lines are packed tightly together, the electric field is super strong. Where they fan out, it's much weaker. It's just a fantastic, intuitive way to see invisible forces at work.
Finally, Section 6, Mastering Physics with AI.
We have covered a ton of ground today. And let's be real, trying to absorb a full textbook chapter packed with vectors, formulas, and massive conceptual leaps, it can be totally overwhelming. But here is a modern study hack: Google's Notebook LM. It's an AI-first note-taking tool. So if you want to really master all this electrostatics material we've been going over, you can drop your textbook PDF right into Notebook LM, and it becomes your personalized, highly focused study partner.
The real game changer here, and what sets it apart from a standard chatbot, is that it is strictly grounded in the sources you upload. Give it your physics chapter, and it becomes an absolute expert on that exact text. No hallucinations, no drifting off topic. It highlights the big ideas in dense reading, generates concise summaries of tricky stuff like Coulomb's law, and can even whip up custom study guides or audio discussions to help you prep on the go.
As you tackle your studies, maybe even using a tool like Notebook LM to help you synthesize this whole chapter, I want to leave you with one seriously profound question directly from today's text. If a charge moves and its push on another charge is delayed because of the speed of light, what exactly is that force doing while it's traveling in between? Does the electric field actually exist as a real physical thing with an independent life of its own, even after the original charge is gone? Think about that for a bit. It is a completely mind-bending feature of our universe. Keep asking those big questions, keep learning, and I'll catch you in the next explainer.